Good afternoon, everyone. My name's Jared Leake and I'm the CEO of Australian Alliance for Energy Productivity, or A2EP. And I'd like to welcome you to this webinar on metering and measurement. May I first start by acknowledging the traditional owners of where I'm living and broadcasting from in the northern suburbs of Sydney, that being the Darramurrugal people, and I pay my respects to their elders past, present and emerging. If you'd like to acknowledge the traditional owners of where you are today, feel free to write the name of the traditional owners in where you're living, just in the chat box. I'll start today's webinar just slightly differently because I thought, you know, with this webinar, it's we can start about talk about sustainability starting at home. And may I share, if you can see my video here, here's one quick one of how I do it at home. TP-Link smart plug with energy monitoring, great $35 product to plug in, and you can start your own metering and monitoring right from home. And for those of you who are new to A2EP, we are a not-for-profit organisation funded by our members, and our members share our mission to double the energy productivity in Australia. In short, energy productivity is about more dollars from less megajoules, and we help take roadmaps and help them become reality. So for today's agenda, we have joining us from Northmore Gordon, we have Chris Warris, along with Hugh McCallum from Coppers. And we're going to start off with a perspective of just why metering and monitoring is so important. After that, we'll have James Rong from Schneider join us, talking about some next generation monitoring devices and how they can be incorporated into your own plant. Followed by that, we have Fadi Geha from Simble and Gareth Mann from MTA Energy. We're going to talk about the systems from Simble and how that's used by an energy manager. That's Gareth from MTA, going to be talking about that product. After that, we're going to step it up with the technology and we'll hear from Iain Stewart from Exergenics. Talking about how Exergenics is using data to create better decisions for chillers and cold rooms and the like. Finally, we're going to finish off with an update from our arena process heating studies. Kevin Joyce from Energy and Thermal Services is going to give us an update on the heat pump project that we're running for Hardwicks, and we'll get an update of what's happening on that one there. So, in this webinar format, please add your questions in the Q&A box down the bottom and then upvote the questions that you like. Yeah, so we'll be able to get right nice and interactive at the end of each session and have time to answer your questions. We'll also stay around after 5 o'clock if we've got some questions left over, and we'll endeavour to get to those then if you'd like to stay around a little bit after 5 as well. So we're talking about metering and measurement today, and I suggest to you that it's the second greatest enabler to getting action on energy productivity projects. The first is no doubt the commitment from board for commitment to net zero or science-based targets. But number two, soon after there, is metering and monitoring, or measurement and verification in other terms. However, it's certainly in my experience, it's often an oversight, an area of oversight. There's plenty of savings and things to come, and everyone knows the famous saying of, you know, what is measured is managed, but it's not always a given that it's done. Certainly in my experience, this may be a familiar story for you, where you have an upgrade project planned, and that upgrade project would deliver X energy benefits and Y productivity benefits. And then a few months after the installation, someone says, are we achieving those benefits? Are we getting that what we thought we would get from this upgrade? And usually the production and the yield, that's known straight away. Yes, we're producing more. But then you ask about the energy benefits and other benefits like this, that we needed metering, monitoring in place. And I suggest, I'm not alone here saying many times, it's, oh no, we overlooked that, you know, the budget was cut a little bit and we didn't quite spend enough in this. And I can certainly say from experience, that really makes it hard for that next project when you're trying to get approval, if you didn't have that data before and after. So yeah, I think this is an absolutely relevant and such an important topic. And so we're taking a look at it today through what's changed, what's making it easier for you to get the data, what's making it easier for you to use the data, what's changed will make it easier to have more power with that data as well. So next time you go to that CFO, you'll have all the data and information you need after what we see today. So without any further ado, I'd like to hand over to Chris Warris from Northmore Gordon and Hugh McCallum from Coppers. Chris and Hugh, looking forward to hearing from your journey over the last few years and how metering and measurement's been important to you. So I'll stop sharing and hand it over to you guys.
Thanks, Jared. I'll just share my screen now. Share.
Yep, that's coming through.
Okay. Well, thanks, Jared, and thanks everyone for joining us. Thanks A2EP for the opportunity to come and talk about this. A little bit about myself and Northmore Gordon. We are a specialist energy consultancy, and we work with a lot of large energy using sites to help them manage their energy costs. So we get to see a lot of different sites, some with good monitoring, good energy metering, and some without. And one of the things we always try and do with our clients is convince them to do to put in more energy metering and monitoring. And most of them realize that it's an important part of energy management, but they struggle to get the business case accepted by management to actually implement the metering. It can be quite difficult because it's a little bit intangible. If you replace a bit of kit, replace a chiller or something, you can estimate the energy savings and there'll be a payback, a nice clear payback. With metering and monitoring, it's not quite so clear cut. You have to spend some money, and then after that, then you can identify some savings projects. So there's often not that direct business case payback from metering and monitoring. So we often talk about the benefits of metering and monitoring, and look, there's lots of material out there that spruiks how important it is. I know that the New South Wales Department of Industry and Environment has a couple of guides on metering and monitoring, and I think everyone understands that, yes, it's important, but I thought what I'd do here is give an example of a real-world case study where a site has implemented some metering and actually got some benefits out of it, and what they did with the data, how they used it, and some real tangible outcomes from it. And I'm joined by Hugh McCallum from Coppers Carbon Materials and Chemicals, who will throw in his first-hand experience on the benefits of having good energy metering. So we'll jump straight over to a little bit about Coppers. It's a chemical manufacturing facility in Newcastle. They take coal tar, which is a byproduct from steel production, and they refine it into several products. The main one being pitch, which then goes over to the aluminium refineries to make the electrodes. So I think of it kind of like an oil refinery, but instead of using crude oil as the feedstock, they use coal tar as the feedstock and separate it into useful components. They're a large energy user. I mean, large is a relative term, but in terms of some numbers, they spend over $1.5 million a year on electricity and over $2 million a year on natural gas. They also have a similar amount of what they call a fuel oil that they use. It's a byproduct from the process, and they burn it in their appliances in place of gas. So it doesn't have a direct cost. It's not exactly free, but they don't get invoiced for it. So it's a complex site with lots of energy using appliances, a couple of steam boilers, a couple of hot oil furnaces, 3 reboilers, they're distillation furnaces, and a few smaller things as well, and a lot of electricity users, lots of large pumps, air compressors, agitators, cooling towers. So they implemented a fairly significant energy metering and monitoring system quite a few years ago now. And so the question is, how did they get that approval? And really it was, they've been on this energy management journey since the old Energy Efficiency Opportunities Program in about 2007, sort of forced them to look at energy. And they did that and realized that there were some benefits in this energy management program. And management then made a commitment to managing and reducing their energy use. And once that commitment was made, they really realized that energy metering and monitoring was really essential to doing that. Hugh, are you there? Do you want to elaborate on how it was got approved and implemented?
So it was done over several years. Some of it was done on like they upgraded some switchboards, and but the underlying thing was there was a commitment to making an improvement, so it became part of the thinking, and it wasn't left out in some of these upgrade projects. And it from practice, you really do need to be able to measure things to understand what's going on and then to make any improvements.
Yep, good one. Thanks, Hugh. So now that they have gas meters on all the 7 main gas users. They have steam flow meters off the boilers, and there's I think there's about 27 electricity submeters that I counted, and it's all connected back to the plant SCADA system, so they can view the data in real time. So some examples of where it's actually been useful. Starting with this first one, it's really helped them to manage their gas MDQ. Maximum daily quantity. So it's a bit of a busy graph, but what it shows is the daily gas use since the start of 2015. And you can see that early on, a few years ago, it was very variable. Daily gas use was highly variable. And what that means is you just can't really get a very good, you can't negotiate a very good gas tariff if you have a demand profile like that. The utilities like a very steady, constant gas use. So with the monitoring, they were able to monitor each of their appliances that was using gas and really get that under control a little bit. I mean, it's still far from perfect, but you can see that over the years, in recent years, it's been a lot more steady. There've been fewer excursions, and they're generally of shorter duration. And because they're now a much more steady gas user, they've been able to negotiate relatively lower gas tariffs. And they've still been hit like everybody else over the last couple of years with the increases in gas prices. But nevertheless, they have got a reasonably good price, and they get less overrun charges. Now, you can really only do this sort of thing if you have real-time, day-to-day or hour-to-hour gas monitoring. It's no use using the gas bill because that comes at the end of the month. And if you've had your overruns, they can be significant. They can be tens of thousands of dollars. So Hugh, do you have any comments on how the metering has helped you with this?
Yeah, so back in before May, our gas consumption increased by 20%. So we were able to identify that very quickly, and we were able to, it's quite a complex plant, but we were actually able to identify that there was a blocked downcomer in one of our distillation columns, a partially blocked fume line, and there was a design fault with one of our fume injectors. We were able to identify that. We understood what it was costing us, and we were able to prioritise it and fix it, and then verify that yes, those were indeed the problems, and we've been able to maintain. Well, we got back to where we were before, so we were able to maintain our normal gas consumption.
Yep, good one, thanks. That actually comes to my next slide, which kind of you've talked about this one already for me, Hugh. But this is showing that increase that Hugh was talking about there. So that they did have this higher use, and the thing was that it was slightly higher gas use, but it wasn't affecting their production significantly. The plant was still running, so it was kind of a hidden problem. And without being able to monitor it and look at it, this could have very easily become the new baseline. Typically, once you have an increase in use, if it goes for 12 months, then it becomes the new normal because the gas bill is the same as last month, same as it was last year, and people start to think that that's normal when it's not. And then, as you said, once you identify there's a problem, then you've got to figure out where it is. And with their gas metering, they were able to figure out where it was, and then quantify what the cost was. So it was costing them over 150 grand a year, which meant they could prioritise actually going in and fixing it. On to some electricity examples. So this is some data from their SCADA system of power consumption on some pumps that they recently put some variable speed drives on. So there's a little bit hard to see here, but there's 6 pumps there, varying sizes, and it's a reasonably complex system. It's running 24 hours a day, pumping hot oil around part of the plant to keep everything warm. And also quite complex or quite expensive pumps. They're magnetic drive pumps, so they're not your standard pumps. So being able to, so that they've put the variable speed drives on this system and been able to instantly see that there's a step change in the consumption of those pumps. And apart from one of them seems to have been had to speed back up again, but the others have maintained that saving. So now that they have confidence and they can see that it's actually worked, there are several other systems that are quite similar around the site. So they'll have greater confidence to build a business case to implement it on those systems. And in fact, I think there's a capital expenditure request in play at the moment to do that on a slightly larger system. The other thing about having this data is that we'll be able to generate energy saving certificates from this because they have the data before and we now have the data after. So for this particular project, that's worth about $40,000. Hugh, do you want to talk about that one a bit from your side of things?
Just makes it easy to justify and see what's going on. So we've done similar things in the past, and on like satellite plants, and we've had to rely on monthly billing data, and there's a big lag between when you make a change and then if you're then seeing the results. In this way, we're able to see them immediately, and if there is any little hiccups or anything like that, you also see them straight away.
Yep, good one. And then the last example, specific example that I've got is sort of recently they had it helped them to identify and rectify an electricity billing error. So again, you might not be able to see this, but on the top right-hand corner there, that graph is data from the utility. So they noticed, or Hugh noticed on the February 2020 bill that their demand had doubled from what it should be, or what he was expecting from his data. It went from normally 1,600 to 3,200. And that means it's an extra cost of about 10 grand a month for having that demand charge. So the utility data up in the top right-hand corner shows that there was a big spike. So when it was questioned with the retailer, they came back with this data and said, "Oh no, here's your data. You did consume this, so we're going to keep charging you." But Coppers had their own data, which is the bottom right-hand corner there, from their own meters that showed that there wasn't a spike. Now, what they realised was that spike coincided with some work that was done by the utility on that meter. It was sort of a week where they were doing some sort of servicing of it. So being able to have their own data and compare it with the utility data, they were able to go back to the retailer and say, "Look, this is not right. Here's the data." And I think they've now accepted that they're in the wrong, and they're in the process of crediting Coppers with that charge. So again, this is an example that you would struggle to see it and justify it if you didn't have the metering. Hugh, do you have any comment on that one?
That's pretty accurate. That's pretty much what's happened. Yeah.
Okay. So there's some specific examples there, but in general, this metering has helped Coppers to manage their energy use, And you can see over, you know, the 10 years or so that they've been on this energy management journey, some actual real results here. So that's, you can see in the red line, a 35% reduction in their gas use, and the blue line, an 18% reduction in electricity use from where they were about 10 years ago. And note the production has been fairly stable over that period as well. So, I mean, it's not a perfect, smooth decline. There's been some reversions there where their usage has gone up, but having that metering has helped them to get that under control again and bring it back down. So if you convert those percentages to dollar terms, you know, it's in the millions of dollars that they've saved in energy use.
Fantastic.
So I had these slides because these are from the OEH metering and monitoring guide, and a lot of people will have seen these, and you know, there's all these reasons why you do it, but hopefully we've shown that, you know, some of these reasons are real. So, you know, coppers have been able to set and achieve their energy targets, establish an energy baseline, identify unexpected increases in energy use, know the impact of each of their appliances. They've been able to monitor the impact of their energy efficiency measures. They've been able to validate retail energy bills, been able to mitigate peak demand on that electricity charge, but also on their daily gas charges as well. Build better business cases for energy projects. They've been able to access energy saving certificates by being able to meter and verify their projects, and yeah, do that measurement and verification of their projects, and generally operate their facility more effectively. And that's the end of my presentation.
Brilliant. Thank you, Chris. Thank you, Hugh. Absolutely. Energy productivity in action there. Great news. Thank you. Just a quick question there we got here from Brent. Are you purely measuring pump energy consumption for this when you're talking about the pump energy savings there?
Yeah, so that was just the the power consumption of the pumps. All they're doing is circulating hot oil around a system to keep it warm. So I guess the service that they're providing is to maintain a temperature in the pipework, and that temperature has remained constant. Gotcha. So they're doing the same job with less power. Gotcha.
And did you consider anything else other than BSDs, like changing impellers or a change of flow control valves at all?
I'll let Hugh answer that, but because my understanding is that they're quite unusual pumps and a little bit tricky. Is that correct, Hugh?
Yeah, that's correct. So we did already do some changes with flow control. The VSD, well, slowing the pump down is much more effective means of reducing energy consumption, and changing the impellers and that sort of thing. I suppose it wasn't really considered in great detail. Again, we were doing, this is another case where we were doing an upgrade of sorts, and we included VSDs in that upgrade.
I think with those magnetic drive pumps, you're reluctant to fiddle with them too much.
Yeah, and the other, I will say this, the other thing about changing impellers and stuff, it's a bit hard to back out of, whereas a VSD, like on one of the pumps, we weren't happy with the performance at the lower speed, so you can just change it back. It gives you a lot more flexibility.
Very good. And James, if you'd like to get your presentation up and running, we'll change over, and we'll if there's some other questions, we'll hit those at the end. I think Stephen had one there. Sorry, Stephen. We'll just keep things moving. We'll take that at the end.
All right,
it's come through. Go for it. Yeah, go for it.
Okay. Good afternoon, everyone. Thanks for this opportunity to A2EP, and my name is James Rong. I'm the offer manager for Power Solutions in Schneider Electric, and the metering energy monitoring system is one of the portfolio I look after in Australia. So today we're going to talk about two things. First, we want to go through and talk about the metering transformation, and also the best practices on how to select the right meter for the right application. Second part, we're going to introduce our smallest smart wireless energy sensor, which is called PowerTag. So first of all, let's have a look the transformation of the metering products. So I've summarized the 5 major transformations of the metering by comparing the products on the market and versus the past. First of all, the metering is getting more digital. So we need more data, and you'll find more and more digital meters, right? Analog meters has the limitations on only monitoring multiple parameters, connectability, data storage, etc. So which can hardly meet the customer's requirements. The second transformation is more connectable. So we have different systems like energy management systems, building management systems can remotely connect it to the power meters. So that requires the meter can support the industry communication protocols, most commonly like Modbus, BACnet, etc. The third transformation is about efficiency. There's 2 different perspectives. One is about the installation. Right? From an installation efficiency point of view, we can use the traditional current transformers, do the hardwire to the power meter. And also the low voltage transformers, current transformers can connect it to the meter via a 1 RJ45 cable. So from that point of view, the installation of the power meter is much quicker and save the hardware and labor hours. From the metering efficiency point of view, if the site has green energy, for example, they have solar panels, they also use the energy from the utility. In the past, you probably need 2 separate meters to monitor the different energy flow. But with the digital power meter, which can monitoring the bidirectional energies, you can use 1 hardware to monitoring these 2 different parameters. The fourth transformation is called multifunctional. You probably will notice the MFM on a lot of single line diagrams, which is called a multifunctional power meters. The meter is not only can record electrical parameters, but also can integrate it with your water gas informations by counting the pulse generated from the water and the gas, and it will get the total pulse times the pulse weight, you'll get the total consumption. Also, the power meters can act as a data storage. It can be a data concentrator to monitor different parameters and log it into its own onboard memory. The multifunctional meter can be an event recorder or sequence event recorder. When events happened on site, it can record events at a timestamp and help you to quickly identify the root cause of the fault. Last but not least is the security. We talk about cybersecurity nowadays, and we focus on the network data security. And how about your hardware? How can we make sure a power meter installed on your network is secure? For example, the metering providers will release the firmwares to fix the bug. How can you make sure the meter only accepts the genuine copy from the vendor, from the metering manufacturer, right, to load into the meter, not a third-party version? So in that case, you can use digital signed technology to make sure the firmware can only be loaded to the meter, which is coming from the factory. So with these 5 major transformations, of course, there's a lot of products on the market. So the question comes is, how can we select the right meter for the right application? There's some good practices, which is called application-oriented metering selection. So we need to understand what exactly customer needs are. So from the very basic requirements, which is energy monitoring, customer probably only focus the kilowatt hours. That's a parameter which linked to the electricity bill. You can find some basic energy meters to install inside the boards to monitor the load. For some large industry sites, they probably need more electrical parameters like voltage, current. They would like to see whether the load current is balanced. They need to know their power factor informations. In that case, you need a proper power meter that can monitor more electrical parameters to help you to understand your network efficiency, understand your network and the load. So for the large critical site, not only the electrical parameters or kilowatt hours, they need to know more about power quality, because power quality will be the root cause or the main cause of the unplanned downtime. So in that case, the power meters should provide them some voltage sag swell informations, total harmonic distortions, transients. So they probably need a power quality analyzer. So with the understanding of the customer needs, combined with the single line diagram on site, we can pick the right meter at the right level in their low voltage distribution network. So this is pretty much the capture of the Schneider Australia's power meter portfolio. I'm not going to talk about these meters today. So I will mainly to highlight the smallest wireless energy sensor, which is PowerTag. We launched PowerTag in 2017 in Australia, and we've sold PowerTags across different segments. Some of them are large critical buildings, data centers, industrial manufacturing, and large commercial buildings, for example. And the others are small buildings like retail stores, residentials, school and universities. So PowerTag can be installed pretty much across all segments. And as long as they have the LV distribution network and they have final distribution boards, help you to manage the energy. Why do we launch this product? The idea for PowerTag is to give you the visibility of the energy consumption down to the circuit level, get as close as possible to the final distribution load. At the same time, PowerTag will provide you the overload alarm, voltage loss alarm. And once you have the information, you monitoring the circuits, the PowerTag can push the information to the energy monitoring system, and you collect the data. Like Chris and Hugh just mentioned the example, you have the gas meter, you connect it to the SCADA system, you get the data information, then you, after analyze these data, you will take some actions to reduce the energy, to improve the energy efficiency. The benefit of the PowerTag are seamlessly designed. So you can install the PowerTag just attached to a circuit breaker. There's no change to your existing architecture. Okay, it's completely wireless between the PowerTag to the gateway. There's no cable at all. And there's no impact to footprint. If you add the PowerTag to the circuits, you don't require to upsize your switchboards. And also the solution is fully scalable. As long as you can add more circuits or circuit breakers to monitoring, to connect to a load, you can attach the PowerTag to the circuit breakers to monitoring that load. As long as it turn on, the time you turn on the circuit, you get a monitored of that load. Last but not least is the easy installation and commissioning. We have the coming slides to show you how easy to attach the PowerTag to the circuit breaker. And the commissioning is all via the web portal. So you can locate the PowerTag, you can pair the PowerTag really easy. This is an example of what kind of device can be installed in the final distribution board. You can have a PowerTag attached to your NSX circuit breaker, or the main circuit breaker tells you the total energy consumption of your final distribution board. And you can also attach the PowerTag on the power and the lighting circuits. So for neighbors' energy efficiency rating, they need a power and lighting separate metered. So in that case, if you put a PowerTag on top of the power section circuit breaker or a lighting section circuit breaker, you will have the total consumption of power and total consumption of the lighting. And the next day, you can attach the single phase PowerTag to the circuits. And for some critical loads, you have the visibility of the energy consumption for that specific load. We also have some PowerTag control modules, allows you to use mobile app to remotely turn on off the circuit breakers. You can, for example, you can control the lights. If you forgot to turn the lights off, you can use a mobile phone connected to Facility Expert small business app to turn the lights on off. And the most critical piece in the PowerTag system is PowerTag Link. So this is a gateway inside the switchboards, talk to different PowerTags, and also it can connect it to your existing network and talk to the high-end system, like energy monitoring system, building management system. Next month, we are going to launch 3 new products, which is PowerTag Rope, PowerTag F160, and a PowerTag Display. PowerTag Rope will monitor the higher current, which is above 630 amp, all the way to 2000 amp. PowerTag F160 will monitor 63 amp to 250 amp. The PowerTag Display is a local display, can show maximum 20 PowerTag real-time values. So with all these new launches, plus existing PowerTag offers, we cover the load current from 1 amp all the way to 2000 amps. The most important is we have the driver, pre-configured driver in the energy management system. The EcoStruxure platform can seamlessly talk to the power tag to get the information from the device. If we do a quick comparison for the wired solution and the wireless solution, the wired solution will require the power meters, the gateways, and if you want to monitor individual circuits, you need to install individual CTs. If you change completely to the wireless solution, there will be promisingly about 20% on the hardware cost savings. And also the installation by using the wireless solution is much quicker, more efficient as well. Next is the installation. There's a little animation here to show you how quickly you can install the power tag to the circuit breaker. You just enter the power tag to the bottom of the circuit breaker. The 2 pins will get the voltage signal. You put the current cable through the hose, will get the current information, and you tie a screw on the circuit breaker. You'll get the information of the current and voltage. Then you calculate the kilowatts and energy consumption. We recommend the installation of the power tag at the downstream of the circuit breaker. When you have the circuit breaker trip, the power tag will have a capacitor inside and send you the voltage loss alarm. And you'll get notified from your mobile phone straight away. So the little power tag is not only give you the energy power consumption, but also tells you the status of your circuit breaker. So, and to wrap up, I would like to talk about a real case example where we've installed a Schneider Electric power tags to help our customer to monitor, control, and stay connected to the retail stores anytime, anywhere, to help them to meet the corporate sustainability targets. I'm sure you've all heard about McDonald's. Well, later this year, they're going to open the 1,000th restaurant in Melbourne, Melton South, Victoria. And to celebrate their 1,000th restaurant, they've decided to design the store in a way that runs on 100% renewable energy. So, and to do that, McDonald's have partnered with Schneider to help them with their restaurant electrical designs. There was a couple of things that we need to keep in mind that when we design the solution for McDonald's, it needs to be scalable and adaptable, considering they plan to roll out to the same solution to other stores, no matter it's retrofitting or a new stores, right? They want a solution that would allow them to remotely monitoring and control their facility. And they will ensure the store managers and the crew members are focusing on delivering the best in-store experience. And lastly, they integrate the solution with real outcome to help to drive McDonald's sustainability target, which is to reduce the CO2 emission by 30%, 2030. There's a number of solutions that falls into this architecture as shown on these slides in terms of effective remote monitoring and control. When you power tag was the best solution for McDonald's because of the ease of the installation, implement, scalability, adaptability, cost effectiveness, and how it can be connected to an open cloud secure platform to provide the insights of every single circuit that has been tagged with a power tag. So to give an idea of what we included in McDonald's 1000 store, so we installed the wireless power tag energy sensors to monitor the energy consumption across all the electrical assets, including their fryers, their HVAC, the drive-through suns, and so on. They have the ambient refrigeration sensors to monitor their cool rooms, freezers, to ensure they're compliant with the food regulations. And the power tag I/O modules allow them to control the lighting. They only make sure the lighting only switch on when they need it to save the electricity. So lastly, power tag are connected to our facility expert, the cloud-based energy monitoring platform. So customer can remotely monitoring this store, and later on when they roll out to other stores, facility expert can monitor multi-site and help them to benchmark which restaurant is most energy efficient, which one is least energy efficient. They can do some comparison as well. So also we launched our Schneider Pacific Innovation Summit yesterday. I'm not sure everyone have joined this summit or not, where we have McDonald's as our guest speaker to talk about their partnership with Schneider and how we help them to achieve their sustainability goals. I will highly recommend. I'll share the link with everyone to watch the video on demand. There's some good story about how they use power tech to achieve the energy savings.
Thanks, James, and we'll be sure to pass that link out next week.
Cool.
Good.
Thanks. At the end, we are very passionate to work with you, design the solutions that can help you to track your energy data, reduce consumptions, meet your sustainability goals, and make the most of your energy.
Excellent.
Thanks, everyone.
Thanks very much, James. That's certainly going to make things easier to get this implemented. Just one quick question. You mentioned retrofitting. The PowerTag only retrofits to a Schneider or Clipsal circuit breaker, or can it go on?
No, we have the universal version PowerTag as well, which can go with the third-party circuit breaker as well.
Excellent. Good to hear. Good one. Thank you so much.
Thank you.
We'll change over now, and we've got Fadi Geha from Simble and Gareth Mann from MTA Energy, and we'll change over the slide here for their presentation, and let's hear a little bit more on also using this metering and using this data as well. All right, Gareth, you're in control.
Hopefully you can hear me. I'm working there at the moment. I'll just get it up for Fadi.
We can hear you, and
it should be.
Yep.
Oh, should be up.
Cool. Yep, we're in business. Go for it.
Thanks, everyone. Thanks, Gareth, and yeah, thanks, Jared and A2EP for giving us the opportunity to talk about Simble and what we do. We're a technology company. We're an energy management systems provider, and we basically work with commercial, industrial type clients. We're offering our solution to energy managers to help them and help their customers understand energy and basically do measurement and verification type projects. If we move to the next slide, Gareth, we'll talk very quickly about the sort of capabilities we offer. We are hardware agnostic. We're very much focused on software only solutions, catering across the spectrum. We recently launched our Simble Home app, which is really aimed at helping residents basically understand their energy and measure and energy usage, understand solar generation, look at battery optimized. So we rolled that solution out into the market in Australia. We also offer our bread and butter capability, which is what we'll talk about, or Gareth will talk about a bit later, which is the case study working with one of his customers, offering our Simble Sense energy and IoT platform with a energy sub-meter capability to provide full energy visibility. We also offer sustainability solutions, which Carbon View is used for corporate sustainability reporting and carbon emissions reporting. If we go to the next slide, we'll see that we sort of cover our headquarters is in Sydney. We also have an office in London working with UK customers and partners, and our R&D centres are in both Vietnam and Sri Lanka, which is where we develop the tech. Our product managers are based in Sydney and in London. And moving on to the next one, just a snapshot of the type of customers that we work with, from small ones, you know, schools, universities, councils, manufacturing companies, multi-site organizations. The key point of what we try and do is make metering affordable for what we would call the majority of customers out there that, you know, we know need to meter, just like the example that Hugh shared with us about the business that he's got, and what Chris talked about from a consulting point of view of the type of data they need. We're all about providing that data in real time into dashboards and apps that users could use across all sorts of locations. I'll now hand over to Gareth from MTA Energy, and Gareth will, as a partner of ours, deployed the solution to one of his customers, and he will talk about that project. Thank you.
Thanks, Fadi. Thanks, everybody. So MTA is one of the new energy retailers in the energy market. We're effectively a group of power engineers. We believe very strongly in data and how data can inform decisions, and we're particularly focused around energy efficiency and demand management as a way of mitigating costs. And ultimately, you'll see coming to the market, the two-way market, where demand-side bidding will become very much a revenue generation, as well as the opposite side of a cost saving. So the diagram you can see is an attempt to try to get the entirety of the concept across to most customers. Because we are operating as a retailer, we feel that we can put a lot of these elements together that generally are treated as in their own separate silos, and quite often the true cost savings are in the gaps in between. So really it's meant to show the journey of cost reduction and consumption reduction. So we start off on the left-hand side, which is really where a lot of the initial analysis goes, which is really around how do you reduce consumption, how do you understand the consumption before you go to any of the other mitigants that you might have, whether that be solar PV or demand control. And from a retail perspective or an energy procurement perspective, generally most people's approach is to try to make themselves look as good a load to a retailer, and that generally translates into make themselves look as big as they should, and we don't feel that's the correct approach. So, but anyway, we use a lot of EMS data, we do a lot of the analysis, then we can control it, and then we look at the access to the wholesale market, and we integrate the whole lot into an ongoing management structure. So this is, I'll show you a couple of screenshots from a customer which has a large warehouse, a headquarters and 60 stores. So we're providing the energy supply to that, and we're using Simble Sense across the entire portfolio. And the type of instrumentation we do and the type of analysis we do depends on where you are. So inside the warehouse, we have, we've got probably six, I think at this stage about 6 sensors installed, about 12 direct circuits that you can see. You can count the direct circuits there. And that's really to understand what was happening in the warehouse, who the bad actors were, what we could do to control them at a circuit level, as James mentioned earlier, once you drive down into that sub-level. And then we also validate a lot of this information from the utility data, actually from the revenue meter data that we can see in MSATs. So even though it's 24-hour delayed when we get hold of it, we've got real-time data relatively coming off of the field from the Simble Sense, and we're using Watt Watchers as the actual device in the field. But we can cross-reference this, and we use that. You'll see that later in the presentation in regards to how we do the benchmarking. So really, you've got to get the visibility and you've got to get the understanding of the site dynamics before you actually go much further, and that's the really starting point. And you can see, just to give you an example here, if everybody can see my cursor, you can see that the forklift charges, it's an interplay between operations, but these are all electric forklifts, and running your forklift is oxygen to a warehouse. So if your forklift's flat or out of gas, then you can't move product. So it's extremely important to make sure you maintain your operational capability. But the operational guys were doing exactly what you expected them to do. They were cleaning up their workplace, and they were shutting down at 2 o'clock, and they were plugging in their chargers so they'd all be ready to go the next day when they came on shift. Unfortunately, from an electrical procurement perspective, that's right at the peak demand period. And so we installed some controllability and some software rules and switches in the background of Simble Sense, which shifted that load from the 2 to 4 p.m. and we actually charged in the after hours. And so a little bit of mucking around because they were running 2 shifts, but we eventually got it to work, and that's been a significant cost saving for them. So you get your control and visibility. The other things that you can, so this is looking at the forklift charges. So we basically, we've got 15 forklifts. We profile them, but effectively we're pulling down in that. This is an Endeavour network, so the demand charges Endeavour are effectively run now between 4 p.m. and 8 p.m. at night, and this is just what we're using the switching for with the relays. You can see the switching rules here in the bottom. We're just pulling that demand down and controlling demand. We can actually do that either manually or remotely, and that gives us a fair amount of control on demand and consumption, but really demand, because we're ultimately looking to the issue of spot market pricing. So you have to be able to, not only are you trying to control your demand tariff, but you're also making sure that you're not purchasing power at the peak period. And so a lot of people focus on cents per kilowatt hour and how much I'm going to consume, but equally important is how you consume the power and when you consume the power. And thinking through those elements is quite important, and that's where metering helps you understand if you go back to the sub-metering. The importance of all of this are cloud-based controls. The Simble system is clearly cloud-based. It's wireless and can be rolled out very, very quickly. So we can instrument a site basically within a couple of days. This is slightly different. It's still brought into Simble, so we bring it into the Simble sense, but this is data that's coming not off the sub-meters on the site, but this is store data. So it's coming from at this stage, we went through the process of looking to get either direct IoT devices in the field, but we found that we could get it more effectively off the revenue meters that were already installed, particularly if they're smart meters. We can get down to nearly real-time data in that regard. And so we start to work down a process where we use Simble for what we call visualization. So ideally what we want to do is we want to check for loads that are, or the bad actors in the loads. And you'll see here, this is an idealized form. And you can see that these loads are occurring outside the operational hours. And the reality is a store has a pretty set load. It should operate between 9 and 6 p.m, for example. If it's got air conditioning loads that are running outside that period, then you've got to chase down and find out why that is. And these can be, they add up into sometimes tens of thousands of dollars a year. And that's a lot of little jumpsuits that the retailer has to sell to make that sort of money. So it falls all the way through the bottom line. And we've found around about 10% of their stores had anomalous pattern behaviour when we started to do the analysis, and we've pulled those out. So we look at pattern matching. And then if you look, we also do a fair amount of data analysis. So this is where I was referring before, that we'll look at the MSATs data, and then we'll look at the Simble data. And we have our perfect store, which is the profile. Sorry, I made a mistake, but I just have to move it to be able to describe the slide. But effectively, we have an idealized store, the gold standard performance, and then we chase all the other outstanding items that are not in the right performance box. And we can use that as a way of bringing the savings back to the client. And you might ask why a retailer is trying to reduce our kilowatt hours that we sell to a client, but that's what our business is. And then if you've got distributed energy resources, we also bring that into the Simble network so that we can visualize what it's doing in terms of total consumption, and also about what the production is, and benchmark the production off the solar system against the standards that were expected for that, so we can maintain and monitor performance in that regard. And we do that as an overall package. We're actually working with an industrial client at the moment, which is not 60 sites but 20 sites, and they will have all behind the meter DER, and we'll bring that into the Simble system to monitor as well. So the benefits for us is the very quick deployment and the capability that it can be out in the field very quickly. It's very user-friendly. It's, you know, the ability to interface with it and use the visualization tools are very strong for us. It's cloud-based, and we're an advocate of data and cloud-based systems. The whole push around IoT and, again, as James and Fadi have mentioned, the fact that you're using digital technology now is really enabling these solutions at significantly lower cost than you would have had even 5 years ago. And, you know, my background is primarily large power generation, and these systems at the industrial level are very fit for purpose, and they're very capable of giving you the data you can make decisions on. Our benchmarking capabilities, we think, is a tool that a lot of the industry should use to chase out all the lazy loads and the wasted energy. We like DER because we see DER as the future of a lot of the grid stability. People think about it as storage and battery systems, but it also talks about how you can demand, manage, control load, and we can get real-time data flow, and that's one of the things we want. So that's our presentation.
Excellent. Thanks, Gareth. And yeah, it looks like this is becoming easier and easier, and energy managers like yourself can look better and better, which is great. Just the one question there from Ahmad asking about specific times for peak power prices. Ahmad, I think I can answer that one. It depends on the provider and the state, and if you have smart meters and things in place. I think I know in New South Wales, I think it's from 2 p.m. till 8 or 9 p.m. That's the peak and other rates, but it depends on the provider.
It depends on the price. It depends. There's two things and one of the other presenters spoke about the utilities. You have to remember the utilities split between transmission and distribution and retailers. But typically the peak power price in the spot market will run in the afternoon, nominally around 6 p.m. And reflective of that demand, the distributors have grid tariffs that typically say anywhere between 2 and 8 p.m, but nominally 4 to 8 p.m. is the peak demand period.
Good. And yes, a question here from Patrick. So for those forklift charges, is Simble able to handle it so that if there was excess PV, you would charge it in the afternoon? But if there was no excess PV, it would then schedule the charge to later at night?
That's correct.
Oh, fantastic. So like the power diverter type option.
Yeah, we can set that. Yeah, sorry, Fadi, go ahead.
No, you're right. No, I was saying there's a rules engine in the platform which allows clients to basically set their own rules based on certain metrics. But yeah, Gareth, you can talk to that. Sorry.
It's your platform, Fadi. Go ahead.
All good. All good. You're the practitioner.
It can be done. Good one. Thanks for the questions there. Okay. Next speaker we've got, and actually building on this even further, Gareth, you mentioned about an idealised store. And I think Iain Stewart from Exergenics is very happy you're using that sort of idea, but I think he might use the term digital twin. Iain, would you like to take over and take us through what you're working on at Exergenics for this?
Sure. Let's make sure that's up there. Thanks. Thanks, Jared and A2EP for the chance to come and talk about what we're doing. So I'm Iain Stewart from Exergenics. We develop data-driven control strategies for air conditioning and refrigeration systems. So we work with asset owners, facilities managers, systems integrators and consultants right across the built environment to deliver more efficient control of complex plant. Today, what I really wanted to talk to you about was firstly our static digital twin, which we're using at the moment, the modelling framework around it, using a pretty standard commercial building central plant as an example. And then I wanted to discuss our dynamic digital twins. This is the what's next piece that we plan to do over the next 3 or 4 months. And this brings in disparate data sets to deliver even more value there for asset owners. So we'll discuss the model architecture and just some benefits, challenges and benefits with each of those. So just at a high level first, To run you through our optimization process, we start with initial data collection, so it's very topical. All of the how do we get this data, we really need it on the other side. So that's always the start of our process, is data collection from the building management system. Then we use that to build a digital twin of the essential plants, the chillers, pumps and cooling towers. So everything really that's sending chilled water or refrigerant around a building. Then we run an optimization loop to generate a more efficient control strategy and work with systems integrators to implement that and then measure and verify energy savings after 12 months. So we'll start with how we do that modeling and the data that we need, and then the control strategy generation. But then I wanted to touch quickly on some of the challenges that we have around that initial data collection and some ways that we might be able to mitigate that. So just as an example, here's a pretty standard low load and 2 high load chiller setup. They're water cooled, so each has a condenser water and a chilled water pump serving it. But for this example, we'll just ignore the cooling towers because it gets adds another level of complexity, and I don't think we have the time. But just on this one quickly, you can see here that these are the part load efficiency curves of both the chillers and the pumps there. And the pumps are reasonably easy on the right. They follow the affinity laws and they're quite well known and easy to model, really. But on the left there, that part load efficiency curve is going to be unique to each chiller. So that's where we need that data driven, and the same can go for cooling towers as well. So having good data to inform that modeling up front really helps us to develop a robust digital twin. So how does this look in practice? So what we do is we essentially take a full central plant and put it into our MATLAB model. So we'll replace all the pumps there with the affinity laws, and then bring in the part load efficiency curves of each of the chillers. But there's another step here as well, and I'll touch on this a bit later with the data side, is that we need to know what are the interdependencies between these pieces of equipment. Obviously, the pumps are serving the chillers. There's got to be a certain differential pressure across the chiller. So we'd go in and look at, well, when are we seeing increases in pump speeds based off chiller loading? So it's just another level of detail down there for the modelling. But once we've got all this in, obviously we've got cooling towers and do condenser water temperature optimization as well. But just for this example, here we've got a simulation tool really. So this is more or less a digital twin, and going from left to right here, if we're doing a simulation, we can input the energy into each of these chillers and then get a thermal load out. So it gives us a simulation tool, and using this we can test a whole lot of different control strategies to see how they're performing. And what the whole system COP is. But it can also be used for replacing chillers or adding VSDs to pumps. Just have a bit more certainty around the decision making there, and reliability on the paybacks to have a really accurate simulation of what our energy benefit will be. But the real value add is in the optimization. So we actually flip that process around and we start with the thermal load as the input into the model, and then the optimization algorithm is deciding how much energy each of these chillers needs to actually service that load. Then we'll run a loop through, and the collation of all of those results forms that control strategy. To give you an idea of what this looks like for this example, as you'd expect here, we've got the low load chiller taking the low load, but yeah, this kind of optimization can be used for things like stage up demand set points. So when do we bring on an additional chiller? Here it's about 850, 900 kilowatts. And then again at about 1700 kilowatts, but also between these stages, we can have load balancing between the pieces of equipment. So this is also saying that we should increase the chiller loading at different rates so that we're maximizing full plant COP. This next graph speaks to that quite well. So you can see there, as the plant COP starts to drop off, the system's recognised about 900 kilowatts that it's more efficient actually to bring on an additional chiller, and that's going to maintain our whole plant COP at a higher level than if we were just to run the low load chiller. So it's quite a holistic approach to think, how can we squeeze out as much efficiency from this system as possible? But there are challenges with this. It's not as easy as I've made it out to be there. And I just wanted to touch on some things that we can consider as energy managers or consultants when talking to systems integrators to make sure that we've got enough data that our plants are optimization ready. So some considerations first and foremost, equipment complexity. So obviously chillers and cooling towers are more difficult to model and require more data than, say, a pump. So around what kinds of data you're going to be storing would you need to be able to model that piece of equipment. But then, as I mentioned before, the equipment interdependencies. So knowing what pump speed we might need to increase a pump speed when a chiller's at a certain loading, that's a really important piece of information when we're looking at these holistic strategies. Also the process speed. So when we're dealing with refrigeration, maybe you've got some short cycling of a compressor and a 15-minute time step has missed something stage up and down. So making sure that that time step of the data that we're capturing is short enough so that we're not missing any processes. And the final one here is the plant seasonality. So if your plant does operate differently in summer and winter, obviously a 6-month extended trend log is not enough data. You're going to miss you shorten your window for optimization to about half the year. So making sure that there's at least a year's worth of data there is, and ideally multiple years of data now that storage is quite cheap and there's cloud-based solutions that can store years worth like Simble. It's, multiple years is really ideal. So some of the benefits we've seen from this sort of optimization. So the first one is up to 20% energy and peak demand reduction without any change to occupant comfort there. So that's really just getting that chilled water out, chilled water or refrigerant through the system using less energy because we're staging up and the right piece of equipment at the right time. There's also improved equipment life. So because we tend to operate more time at part load, there's less stress on the compressors and the pumps from running at really high loading. So you can expect an increase in equipment life. And finally, more informed CapEx decision making. So with that simulation tool, we can go and say, okay, if we've got the part load efficiencies for a new chiller, let's pop that in and see what kind of energy savings we're getting to put some really good numbers around that payback. So that's what we're doing at the moment with the static digital twin and developing these strategies that are reacting to things like thermal load and wet bulb temperature, for example. But I just wanted to extend this idea. This is sort of the where we'd like to go and we'll be doing over the summer. So this is the idea of the dynamic digital twin, and it still uses that static twin as the basis there. But then what we're trying to do here is to bring in disparate data sets and try to have some smart control in real time happening in the cloud. So where previously we used supervised machine learning, which allows us to make inferences given the data set about what a surface or a curve might look like. This is using reinforcement learning. So we're able to essentially set the rules of the game and then let the algorithm come up with a strategy in real time about how best to control this plant or site. So to run through the example here, obviously you'd want to bring in a weather forecast so that you can start to predict thermal load, but also the wholesale energy price, which I'm glad is being spoken about a fair bit today. There's some really big opportunities here that are getting bigger, and I just want to touch on this. This was from Melbourne on Monday, or from Victoria on Monday, sorry, but you've got a really decent chunk of time here in the morning and early afternoon where it was at about $8 per megawatt hour and a dip into the negative price there. And this is becoming more and more common, and I might just touch on why that is. So this is quite a famous curve, the duck curve, which I'm sure many of you are familiar with, but shows the demand from large scale generation year on year decreasing quite significantly during the daylight hours. And this is because this is from California, but the same thing's happening across the NEM. So we've got a reduction in demand for those large-scale generators because of all the distributed solar PV and the actual large-scale solar PV as well is driving that down even further. So what's the impact on wholesale prices and the trends we're seeing there? This is a bit closer to home. This is from Queensland, but something from AEMO last year that showed the important one to see here is this piece in the red or the pink, where the top is 2018, and you can see the frequency of negatively spot priced electricity. And even in 1 year there, you can see that the frequency of getting those negative price events is increasing quite significantly. And this is a trend that I think is going to continue for the next couple of years. So it sort of provides a bit of an opportunity there to control our plant a little bit smarter, to be able to derive some cost savings from this. And the example we've got here is a cold storage facility. It's a really good test case. So in this hypothetical cold store, we've got a temperature set point of -27, but we've got maybe an acceptable range of -25 to 35 and an insulation R value of 50. So this really is almost like a big battery. We've got the potential to store thermal energy in there, or the lack of thermal energy. And you've got charge and discharge efficiencies and storage efficiencies, just like you would have for a battery. So the idea here, I suppose, is to think about load flexing and how can we shift that load away from the expensive wholesale prices and towards those negative or low cost wholesale prices. And some additional considerations might be, well, do we have on-site renewables? As was mentioned before, we want to maximise the use of those rather than export them at those discounted rates. And to add even more storage potential or even redundancy into the system, is phase change material a good idea? Should we add it in? And then maybe if you're changing phase at -30, you don't even have to bring the temperature down as far. So when you're bringing this all together, this is just an example of what that system might look like. And if we imagine it's 8 AM on this given day, we've got real-time feeds of weather forecasts and wholesale energy cost forecasts from AEMO. And this system is in real time developing a temperature set point and a space temperature forecast that it would cost optimize essentially over the full day. So it'll be iterating over and over again to try and maximize time where you're using cheap electricity and minimize time where you're using expensive electricity, particularly if you're with someone like Flow Power who offers to pass through the wholesale cost direct to the consumer. So here you'll see that when that space temperature is higher than the temperature set point, obviously you're going to be ramping up your equipment to try and drive down the temperature. And that corresponds to the time when you've got those negative wholesale prices. So they're actually getting paid to use that energy. And the opposite's true for the afternoon when you have that spike and the prices get up to $70, $80, $90 a megawatt hour. You can actually stage right down your equipment and let that temperature creep back up to that -27. So some pretty significant savings potential there. So we don't yet have data for this, but we're looking for it. But from the back of the envelope calculations, we're looking at around 40% reduction in direct energy costs for a large cold store facility. But there's some other benefits as well. Obviously, they're maximising the use of on-site renewables to reduce using energy from the grid is great. And these systems can also be easily integrated for demand response markets once you've got that those smarts in there that can stage up and down equipment or respond to temperatures. It's pretty easy to take that next step into demand response. And just as a quick call to action, we are seeking data sets and partners to train those algorithms. So we're looking to publish a white paper on this dynamic digital twin just to see what kind of savings, what kind of real world savings we can get with these kind of algorithms. So if anyone's got data sets that they're interested in taking a look at, we'd love to have a look at them. And that's it from me. Thanks.
Yeah, fantastic, Ian. It certainly gets your mind going. You're thinking, you know, how many variables can you put in there? You know, if I knew I had a big in my cold store, I had a big load, a few truckloads coming in at 1 o'clock. Can you prepare for that? I mean, it just seems like you've got a potential platform there that can really handle so many different scenarios. Good. Just check on the questions there. I think we've got a question come through from Patrick again. Can you tell us how many buildings you have created twins for and types of buildings?
So we've been about 10 or 15 at the moment. So we've worked through Monash University. We've got a couple of sites there that are up and running, and we're looking to roll out on about 5. I think the modelling's done for 2 or 3 Melbourne Uni buildings as well. And then we've got a fair bit of data in the pipeline for some other facilities, and then 2 Coles stores and 4 refrigerators, or 4 racks per store. Oh, sorry, 4 racks total there, and a few other little bits and pieces, one in Melbourne and one in Perth.
Brilliant. So I think it's pretty clear, looking for some more data and more cases to run and get the dynamic twin up and running real soon.
Absolutely.
Fantastic. Good timing for this. Before we go to the arena stories, I think we'll just knock off this session with Stephen Sizer's question. And this goes back to for Hugh and actually for Chris, just a quick one on the those implementation of those VSDs. Was there any adverse impacts on the power quality when you did that?
Hugh, you want to take that one? Yeah, as far as we know, there's been no sort of harmonics impacts. Everything seems to be running. I think there was some power quality tests done a few years ago by Chris, by the way, Hugh.
Yes,
and,
so we have power factor correction systems, but I don't believe there's any issues. I'm not aware of any anyway. So there is technical problems with VSDs, like they're not super simple, and they take a bit of getting used to, but overall they're a big benefit to us.
Good one. Good to hear. Actually, I think we had a question in the chat here from Penny for yourselves as well. She put it in the chat rather. Now, was there any formal measurement and verification reports done? Chris, I guess that's on.
They're in progress.
Okay.
We have to do that to create the energy saving certificates. So we're in the process of doing that right now.
Good to hear. Good. Very good. And look, our last section today is an update on the arena work that we've been doing. This is on using renewable energy for process heating. The program's been running for about 18 months, and we've done 20 feasibility studies, and we've run now into 7 feasibility studies. And this is all about using renewable energy to replace process heating. One of the main products available to do that is heat pumps. And we invited Kevin Joyce along today, who's in the middle of a feasibility study for an abattoir. And Kevin, you're working on that project now. You've done the pre-feas and going through the feasibility. I thought it'd be great for our listeners to have an update on what's happening with that feasibility, and let us know how that's progressing. And then once we get through that, we'll talk about how that fits into metering and monitoring as well.
Can you hear me okay?
Sure can, Kevin. Go for it.
Okay. Yeah, this project, I think, just to give you a bit of a background to it, Hardwicks is, as Jared said, a medium-sized meatworks. It uses about 7 million kilowatt hours a year, so it's a mid-sized company, about 42,000 gigajoules of natural gas a year. So the whole aim of the project, they've been quite progressive. For example, they've got 1.5 megawatt of photovoltaics, field-directed photovoltaics already operating at the site. Produces just over 2.3 million kilowatt hours a year of that 7 million that I'm talking about. So it's a significant hit. They're now putting in another megawatt and a 2 megawatt hour battery that's supported by the network. So they've gone a hell of a long way on that side of the fence. They're very progressive. They want to look at what else can they do on the fuel side, the natural gas side, because really they have done some good stuff there. They put a very high efficient boiler in about 2 years ago with a thermal storage tank, and did a lot of work, but really we're only chasing 5–10% sort of thing with those sorts of initiatives. So the next stage is really, can a heat pump work in this application? And with A2EP's support, we've had a look at all sorts of options. And the one we've landed on really was probably where we should have been in the first place. It's a ammonia-based system running off the existing ammonia refrigeration plant. There's, like all these plants, they have 2-stage ammonia systems, and we're putting a heat pump, an ammonia heat pump, on the condenser circuit of that system. It's about 1,000 kilowatts, so it's a reasonably large heat pump compared to others. It pulls a bit, it has a COP of an operational POC, we'll get into arguments later, but of about 5, just under 5. So it's about 200 kilowatts, 190 kilowatts that we'd be using. But given the high capital of a lot of these heat pumps, we really have to work this thing very hard to really get the paybacks to where they need it to be. So I guess standing back from it, we've sort of said we want this to run as a slave. So what it does, it sits there extracting heat out of the condenser of the main system, extracting about 850 kilowatts, which is a significant amount of reduction off the condenser system that we needed anyway, providing the megawatt of thermal energy into the hot water system. It's replacing a 2 megawatt boiler. It's a 1 megawatt plant. So we needed the thermal storage. Luck would have it that Mark Hardwick, who's quite innovative with these things, he already bought, as a part of that project last year, a 65,000 litre tank, and we've now been able to got another one, a 95,000 litre. So we've got 165,000 litres of storage capacity. So the concept is that the thing runs 24/7, 5 days a week during production, and runs as required during the washes on the weekend. So it gives us the capability to do a massive amount of preheating. It's designed for a delta. We've got a delta temperature of about 75 C in the water. We've designed it at 11. We'll get a lot more than 11 as cold water in. But that's a sort of design condition. We need 82 to 83 degree water. So that little bit of topping we're doing with natural gas. The impact of that is about a 75% reduction in the gas usage at the site. Because it's running all the time, it's the only user of gas at the site. So really, rather than get too complex, we've got a slave working as hard as it can to knock off the gas consumption. So that's the general principle of the thing. Some of the operational issues around that, clearly we can't take too much heat out of the condenser, otherwise we'll mess up the main refrigeration system. So we need control interface. The heat pump we've got's got a VSD on it. We'll be managing the amount of power that unit will operate to ensure that we don't impact overcool, if you like, the condenser system. We're pretty safe there because normally the average condenser load's about 1500 kilowatts and we're pulling 800 kilowatts out. So I'm perhaps being a little bit conservative, but the last thing you want in one of these works is to upset the main system. So that's how it generally works. Some of the options around this, look, we're going to run it as a base load, as I was saying, but there's massive flexibility around it. Given that the thing, with the storage capacity we've got, we can either fill the tanks to the maximum, or we can run them at half load, or we can do all sorts of clever things with them. But we can use it as a massive battery. We'll have 2 batteries on site then. We'll have the 2 megawatt battery, and we'll have 160,000 litres of thermal store. That will enable us to, people mention the demand side initiatives that are going to come in place next year in October here, where the retailers and others will be able to bid in. We'll be able to make decisions on when we want to build that tank, so we don't have to build the tank at any time. We can drop the tank if we want to reduce the demand on the site. We can either, for example, on the Friday, we can turn the pump off, and we can just draw down the tanks on the last shift on Friday and build it up on Saturday and Saturday morning at off-peak rates. So all of that flexibility is in there. So look, I think it's a reasonably good thing. We're adding a couple of other things there, like heat recovery off the oil coolers for the existing refrigeration system. The increased condenser capacity will allow us to also put in floating head pressure control on the main ammonia systems. We've always been constrained with condenser capacity. This will enable us to operate more floating head pressure control going forward. So all of those things will be merged together.
Good one. Thanks, Kevin. Just a quick question, any VEECs or ESCIs generated for that one. And to my understanding, you don't. That doesn't happen from a heat pump project. Maybe you can create some ACUs, but not so much these other the other opportunities there.
Yeah, I think we're going to try for a PBA next year with the V. Mainly on the gas offset rather than anything else. You know, we're gas savings can be claimed. So I think we could, provided we can demonstrate an offset of carbon, I think we should be able to claim a VEET certificate. But well, let's see. But that's an added value that we've got up our sleeves, Joe. It's worth about, I've just worked it out roughly on the 10-year depreciation thing, about 100 grand or something like that, which is not too bad.
Nice.
And there's not that many of these things actually happening at that scale. It does then predicate that we need to do some verification and metering, and that's one of the things that we'll have to factor into this exercise. The metering on this project at this stage is not as good as it could be. We need surprise, we need decent mag flow meters. We need a couple of kilowatt-hour meters. We need a lot of temperature meters, a temperature and humidity sensor for the refrigeration. But all that, you know, it's not that expensive, given that we've got a good SCADA system in place already. The plant has a EMS, you know, they measure the power usage and all sorts of things, and all the energy usages to the end users. One thing that does have to happen though is it is sort of operating in a silo at this stage. So in other words, all the good work that's been done on the photovoltaics and the battery and this really aren't joined together, and that's one of the exercises that will have to happen. You know, like any of these large solar systems, there's very good data collection, but it doesn't interface smoothly with the work that we're doing on this side of the fence.
Yep.
So that's a part of the exercise.
So get the metering right. You've got the major tool there in the heat pump itself to be able to do load shifting and demand response, and yeah, hell of an opportunity to save energy there. Brilliant. Thanks very much, Kevin. The project's really good, and we look forward to watching that one over the next many months. So thank you all. And just before I move on to and share with you our upcoming activities within A2EP, just like to say thank you to all of our speakers today. Chris and Hugh, thank you so much. James, much appreciated. Fadi and Gareth, well done. And Iain, thanks very much and for your presentations and discussion with Kevin today as well. Much appreciated. I'll just share my screen now and just let you know what we've got coming up with A2EP. So we have our major annual event here coming up between the 9th and the 12th of November. It's only just going to be in the mornings. That's why it's called the Innovation Express. We're not intending to take up your entire day, but we'll start off with day one, hearing from companies that are committing to net zero and how that is a fantastic enabler to seeing energy productivity projects go ahead. Day two, we'll talk about strategic investments for energy productivity. Day three will be the low-hanging fruit and the high payback and quick win energy productivity opportunities out there. And day four, we'll be hearing from SV and DPI and the federal government there about what they're doing to help you get these projects happening. So that's a great event we've got on the 9th to the 12th of November. That's free for members. That will have a daily cost there for an event cost for those people that are not members, but it's going to be a fantastic couple of days, and we welcome everybody to join us there. Other quick events there, we've got a closed event just for Sydney Regional Councils, just to let you know that the heat pump push still continues, but we're looking to work with aquatic centres next. I think that's one of our top 5 priorities for decarbonisation of process heat. So we're going to talk to regional councils in New South Wales and look at rolling that out further afterwards as needed. 19th of November, we'll also have an event there just to update on energy users, and we'll hear from Tenant Reid and a few other energy users and what's happening there. And then later in the year, just on a date to be finalised, we're going to have a compressed air system workshop with various energy managers and compressed air auditors, let you know the latest there. So that's it from us at A2EP today. I'll just stop sharing this one. Thanks everyone for joining us. Once again, thanks to our speakers, and you'll have the recording of the webinar out next week along with the slides as well. So I wish you all a very pleasant afternoon, and look forward to seeing you again soon. Thank you.